Swayam Prabha. Digital India. Educated India.
In the previous lecture, I have shown you that the rigid body dynamics is described by this equation, and we applied it to certain situations in which omega was a constant. Not only was it a constant, its components along the principal axis were also constant. In that case, we saw that dl dt was really nothing but omega cross L only, and this we wrote as omega 2 omega 3 I3 minus I2 I plus omega 3 omega 1 I1 minus I3 j plus omega 1 omega 2 I2 minus I1 k, where I, j and k are the unit vectors along the principal axis of the body. The principal axis obviously rotate with the body, and this was purely due to the rotation of the body. In addition, I also explained two demonstrations to you. One was the precession of a rotating wheel. When we put this point on a stand, the wheel started also precessing about this axis. I also explained to you the gyroscope, how the gyroscope spinning wheel aligns with the outside frame omega. Before we make this lecture more quantitative, let me explain to you another demonstration. If you recall, we had a demonstration where I had a track like this on which I let 4 cylinders roll, and we found that only one of the cylinders could really negotiate all the tracks and go all the way through. Let me show that demonstration to you again, and then we'll explain it. I have these 4 cylinders here of different shapes, and what we see is that if I roll the straight cylinder down, it does not really go through and falls off the track. It cannot really turn with the turning of the track. Similarly, if I take this cylinder, which is shaped as you can see like this, if it goes, it turns only in one direction. This one is also similar, except that we have given a bulge in the middle, and this also turns only to one direction or falls off. The only cylinder that goes and negotiates curves in both directions is this one, and let us see this. Let us now try to understand why only one particular shape goes on the track all the way, negotiating all turns, both turning left and turning right, and others cannot. The 4 cylinders that I had were: one, the plain one; another one which was like this; third one which was like this; and the fourth one which was like this. It was this cylinder that went all the way. Let us understand why it happened. When the cylinder is rolling on the track, let us take the rolling direction to be this. Then when the cylinder is here, its angular momentum L is in this direction. As it goes around the track, its angular momentum becomes this, and therefore there is a change in the angular momentum in the direction opposite to its motion. On the other hand, when it turns the other way, if the cylinder is here, again I am taking cylinder moving this way, then the angular momentum is in this direction, and when it reaches here, the angular momentum is in this direction, and therefore the change in the angular momentum is in the direction of the motion. This is delta L, delta L. On the other hand, when it's turning on this track, it requires a centripetal force in the direction to the left, and on this track it requires a centripetal force in the direction to the right, so that its center of mass moves properly on the track. Where do these forces come from? These forces are provided by the normal reaction on the cylinders due to the track, and let us understand how the interplay between these normal reactions and the torques they provide really help only one particular cylinder to negotiate all the curves. Let us first take the example of a plane roller where the normal reaction is going to be like this, perpendicular to the surface of the cylinder, and therefore whether the track is going this way or this way, there cannot be any component in this direction. There is no component of these two forces, N1 and N2, and therefore the normal reactions cannot provide a proper centripetal force, and the plane cylinder does not turn at all, it just goes straight. How about the cylinder which is shaped like this? The two kind of tracks, two turns we are looking for are like this. In this case, remember, delta L is in the direction opposite to the direction of motion, and this is F centripetal. In this case, the change in the angular momentum delta L is along the direction of the motion, and this is F centripetal. Let us look at this cylinder from behind. Then the normal reaction on this side would be N1, and on this side would be in this direction N2. If the centripetal force has to be to the left, you can see in this case N1 has to be greater than N2, and therefore the center of mass can turn to the left. On the other hand, if N1 is greater than N2, the torque due to N1 is also going to be greater than torque due to N2, assuming they are equidistant from the center of mass. However, torque due to N1 here goes into the cylinder, and on this side it comes out. Into the cylinder here means, since I am looking from behind, it's along the track in the direction of motion. This is tau N1 and this is tau N2. Tau N2 is smaller than tau N1, and therefore the net torque would be in the direction of motion, which is opposite to the required direction for delta L to change in the direction opposite to motion, and therefore this cannot make the roller turn this way, and therefore this cannot negotiate the curve. Let us see it in the other case. If it has to turn to the right, then this is N2, this is N1. In this case, since the centripetal force is to the right, N2 has to be greater than N1, and therefore torque due to N2 would be greater than torque due to N1. Torque due to N2, as we saw earlier, is coming out of this plane, therefore torque due to N2 is in this direction, and this is larger than torque due to N1. Again you see that tau 2 minus tau N2 minus tau N1 is in the direction opposite to that required to cause this change in delta L, and therefore it cannot negotiate this turn going to the right also. Therefore this cylinder does not go over the track properly. Now we come to the cylinder which went all the way to the track and which was shaped like this. Again, remember, delta L direction is this, therefore torque has to be in the direction opposite to the motion, and this is F centripetal, and on the track turning to the right, this is F centripetal, and delta L direction, therefore the torque direction has to be along the direction of the motion. Now in this case, N1 and N2, the normal reactions are going to be like this, and since the centripetal force is to the left, N2 should be greater than N1, and therefore torque due to N2 is also going to be greater than torque due to N1. But torque due to N2 is coming out, torque due to N1 is going in. Looking from the back side, torque due to N1 is in this direction, torque due to N2 is in this direction, and this is greater than torque due to N1. So the difference is in the direction which is proper for delta to cause this change in delta L, and therefore this cylinder can easily turn to the left. Let us see what happens when it is negotiating a curve going to the right. In this case, again making the normal reactions N1 and N2, we see that F centripetal is to the right, and therefore N1 should be greater than N2, and that means torque N1 is also greater than torque due to N2. Torque N1 is going into the cylinder, that is in the direction of motion, and torque N2 is coming out, and therefore this torque is greater than torque in the opposite direction. And you can see again that the difference is giving the right direction for delta L to be along the direction of motion, and therefore this cylinder can negotiate both the turns going to the left or going to the right, and as you saw in the demonstration, it went all the way through. So this demonstration is essentially to show you an interplay between forces, change in the angular momentum and the required centripetal force that can make a particular roller go all the way along a track and some other rollers not along the track. Let me now go to the general case and ask what happens if the angular velocity of a rigid body rotating also changes. For this, we again go back to our old friend, a rod with two masses on its side rotating about an axis at an angle theta. Recall earlier that we had solved this problem with dl over dt equals omega cross L, because omega was not changing with time. In addition, omega had constant components along the principal axis of the body, which I took to be x in this direction, y in this direction, and z therefore coming out. Let me now see what happens if I also change this omega with time. In that case, recall that the component along the x direction is I1 omega 1. So if I change the omega, the angular velocity, omega 1 is going to change, and therefore L1 dot is equal to I1 omega 1 dot. In addition, there is a change in the component of angular momentum in direction 1 because of this rotation, which we earlier wrote as omega 2 omega 3 I3 minus I2. This you recall we had been using. So there are two sources of change in the component of angular momentum along direction 1. One because angular velocity itself is changing, and two because L is not in the direction of omega, and therefore it rotates about the angular velocity. So notice L1 itself is only I1 omega 1, but when we take its change, it is caused both by the change in omega and by the rotation of L vector around omega vector, and therefore in general I am going to have L1 dot, which is same as dL1 dt, is equal to I1 omega 1 dot plus omega 2 omega 3 I3 minus I2. Similarly, L2 dot, the change in direction 2 would be caused by change in the component of angular velocity along direction 2, plus because L is rotating, that change anyway is caused. So, omega 3 omega 1 I1 minus I3. Same thing for L3 is going to be I3 omega 3 dot plus omega 1 omega 2 I2 minus I1. Although L1 is equal to I1 omega 1, L2 is I2 omega 2 and L3 is I3 omega 3, because as the body rotates, L also rotates about omega, that causes these changes, and in addition the change of omega itself causes these changes. The net is the sum of these two, and therefore this is how the components of angular momentum along the 3 axis change. This obviously then must be equal to the component of torque along principal axis 1, this must be component of torque along principal axis 2, and this must be component of torque along principal axis 3. These equations are nothing but writing dl over dt is equal to tau by taking components along the principal axis of the body. So, tau 1 should be dl1 dl over dt along principal axis 1, and that comes out to be I1 omega 1 dot plus omega 2 omega 3 I3 minus I2. Similarly, tau 2 comes out to be I2 omega 2 dot plus omega 3 omega 1 I1 minus I3, and tau 3 comes out to be equal to I3 omega 3 dot plus omega 1 omega 2 I2 minus I1. I remind you again that although L1 is I1 omega 1, L2 is I2 omega 2, and L3 is I3 omega 3, the change in these components involves both the change in omega component itself as well as a change due to the rotation of L vector around the omega vector, and therefore the net change happens to be the sum of these two. These are known as Euler equations. It is because of this term that the solution becomes very interesting, and this is what we are going to see. As you had already seen in some demonstrations, because of the distribution of velocities, because of the angular momentum, the motion of rigid bodies can sometimes be very counterintuitive, and these equations involve all that in this. If we solve them and interpret them properly, we get all the answers. I also want to remind you that you had been solving the Euler equations, or we had been solving the Euler equations in the previous lectures without formally calling them so. So let me write the equations again. Tau 1 equals I1 omega 1 dot plus omega 2 omega 3 I3 minus I2. Tau 2 equals I2 omega 2 dot plus omega 3 omega 1 I1 minus I3, and tau 3 equals I3 omega 3 dot plus omega 1 omega 2 I2 minus I1. where the directions 1, 2 and 3 refer to the principal axes of the rigid body, and omega 1, omega 2, omega 3 are the components of the angular velocity along those axes, and omega 1 dot, omega 2 dot, omega 3 dot are the components of change in omega along these axes. We will now apply these equations to some other examples and see what we get. The first simple case that I take, when the external torque is 0. If the external torque is 0, then the equations that we should be solving are I1 omega 1 dot plus omega 2 omega 3 I3 minus I2 is equal to 0, I2 omega 2 dot plus omega 3 omega 1 I1 minus I3 is equal to 0, and I3 omega 3 dot plus omega 1 omega 2 I2 minus I1 is equal to 0. This would be the case, for example, if I take this box and drop it down after giving it some rotation. About the center of mass, there would be no torque because the gravitational force is acting on the center of mass. So it will be a torque free rotation. Let us see what do the equations predict for us. In the case of this box, you can see there are three principal axes. One axis is going like this, one is like this, and one is perpendicular to this. The I1, I2 and I3, all three are different in this case. So let us see what do these equations predict. For simplicity, I will take I3 to be greater than I2 to be greater than I1. It really does not matter because I can just name the axis about which the moment of inertia is the largest as axis number 3, the one which is intermediate as axis number 2, and one which is the smallest moment of inertia as axis number 1. So let us first take the case if I give it a spin omega 1, large, and very small omega 2 and omega 3. That is, I give it a spin about the axis about which the moment of inertia is smallest, and that probably would be this axis, and I give it a rotation. Along the way I can give some rotation because I am spinning it about axis 2 and axis 3 also, and let it go and see what happens. In this case, the equations would be I1 omega 1 dot plus omega 2 omega 3 I3 minus I2 is equal to 0. Since omega 2 and omega 3 are very small, I can in the first approximation neglect this. Remember, I am just trying to give you a qualitative picture of what is happening, and therefore I can write I1 omega 1 dot is equal to 0, or omega 1 is a constant. Therefore, if I give it a large spin about the axis around which the moment of inertia is smallest, it will go with constant angular speed about that point. It will keep on rotating constantly. What happens to omega 2 and omega 3, which are very small to start with? Let us see that. So the equation for omega 2 and omega 3 is I2 omega 2 plus omega 3 omega 1 I1 minus I3 is equal to 0, and I3 omega 3 dot plus omega 1 omega 2 I2 minus I1 is equal to 0. Let us differentiate this once more so that we write this entire equation in terms of omega 2 alone. I would have I2 omega 2 double dot plus omega 1 is already shown to be a constant, omega 1 omega 3 dot I1 minus I3 is equal to 0. This is equation number 2, this is equation number 3. let us substitute for omega 3 dot from equation number 3 to get I2 omega 2 dot plus omega 1 I1 minus I3, and now substitute for omega 3 dot, it will be minus sign, so I will write this as I1 minus I2 omega 1 omega 2 divided by I3 is equal to 0. So, the equation I get is omega 2 double dot plus omega 1 square, I have multiplied this and this, I1 minus I3 times I1 minus I2 divided by I3 omega 2 is equal to 0. This is the equation that determines time evolution of omega 2. Notice, since I1 is the smallest moment of inertia, I1 minus I3 is negative, and so is I1 minus I2. Two negative quantities multiplied would give me a positive number, and therefore, I should also write I2 here because I have divided by I2, and therefore I get the equation for omega 2 as omega 2 plus some positive number, let us call it omega square times omega 2 is equal to 0. And the solution for this I know is omega 2 equals some constant A sine omega t plus B cosine of omega t. So, as the body would fall, omega 1 would be constant, omega 2 would be just changing periodically. How about omega 3? I will leave it as an exercise for you to show that omega 3 would also change in the similar manner, sine omega t plus cosine omega t with some constants in the front. Again, using the fact that I1 is the smallest of the moment of inertias, and therefore, if I give it a spin about axis 1, omega 2 and omega 3 would change slightly, they will change periodically, so it will shake a bit, but it will move with constant angular speed about axis 1. This also, the second part I will leave as an exercise for you. If initial spin is given about I3, that is largest moment of inertia axis, you can again show that omega 3 would remain a constant and omega 1 and omega 2 would be changing in this manner. Let us see now the case when I give omega 2 about axis 2, which is intermediate moment of inertia axis, and there is some small omega 1 and omega 3. So, again we will see that I2 omega 2 dot plus omega 1 omega 3 I3 minus I2 is equal to 0. This I can neglect in the first approximation. So, omega 2 is a constant. How about omega 1 and omega 3? I would have I1 omega 1 dot plus omega 2 omega 3 I3 minus I2 is equal to 0, and I3 omega 3 dot plus omega 1 omega 2 I2 minus I1 is equal to 0. Again differentiating this equation once more and substituting for omega 3 from here, we get I1 omega 1 double dot plus omega 2 we have already shown is a constant, omega 2 omega 3 dot I3 minus I2 is equal to 0. Substitute for omega 3 dot to get I1 omega 1 double dot plus omega 2 I3 minus I2 times, this I can change sign when I go to the right side. I can write this as I1 minus I2. So this should be I1 minus I2 divided by I3 times omega 2 omega 1 is equal to 0, or omega 1 double dot plus omega 2 square I3 minus I2 times I1 minus I2 divided by I1 I3 omega 1 is equal to 0. So what we did is really substituted for omega 1 double dot, omega 1 dot, what we did really is we differentiated equation 2 once more and substituted for omega 3 double dot from equation number 3. And the final equation we get, let me rewrite it, is omega 1 double dot plus omega 2 square, which is a constant, I3 minus I1 times I1 minus I2 divided by I1 I3 omega 1 is equal to 0. Since I1 is the smallest and I3 is the largest, this number is positive, and I1 is the smallest and I2 is intermediate, this number is negative, and therefore this entire quantity is negative. Let me write this as omega 1 double dot minus omega square omega 1 is equal to 0, and the solution for this is of the form A e raised to omega t plus b e raised to minus omega t. So whereas earlier when we gave spin about the axis which has the smallest moment of inertia or the largest moment of inertia, the other two angular moment angular velocity components were just changing periodically slightly. Now omega 1 grows exponentially. You can similarly show that omega 3 would also be proportional to e raised to omega t. I will leave this as an exercise, and therefore if I give it a spin about axis number 2, which is the intermediate moment of inertia axis, omega 1 and omega 2 would grow, and you will see that the body after some time does not really rotate about only one axis, but it will rotate about all three axes. Let us see this. I have shown this demonstration to you in a lecture 2 or 3 lectures earlier. I will show it to you again now. So what we predicted is, if I give it a rotation about axis about which the moment of inertia is smallest, it will go without really developing any angular velocity about the other two axes. Let me show that in slow motion. See, it goes down straight. Similarly, if I take the axis about which the moment of inertia is the largest, which will be axis like this, perpendicular to this flat plane, in that case also we saw that the other angular speeds don't really develop much, and you see that it comes down flat. On the other hand, if I take the intermediate axis, as it rotates, the other two angular speeds also gain, and you will see as it falls down, it will start rotating in a manner which will give it rotation about all three axes. You see, it develops angular speed about all three.